Good morning, ladies and gentlemen. Let's do this now. I want you guys to find the angular frequency of the spring/mass system I'm going to show you. What the hell is angular frequency? Have you already forgotten? Okay, so we have here, let's see, this is 5, 6, this is 700 grams. Not seven, wait.
Well, you got the
25
grams.
I was like, didn't we say it was 725?
Plus 500.
So how many kilograms is that?
600, 700, 725 grams.
That's 0.725 kilograms.
Yep.
Okay.
So write this down in your notes. The mass is 0.725 kilograms. And what we want to do is find the angular frequency.
Okay.
So what else do we need to do here?
Well, we know that the angular frequency is equal to 2 pi over t, which is equal to 2 pi frequency. We can figure out the
period. What is the period,
right?
boys and girls?
Well, the period is the second for one cycle. So let's see if I can do this. Let's see if I can get this thing going here. Oops, reset there. Okay. That look like promising right there?
Boing, 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 boing,
One,
boing.
two,
We got some
we
swinging
do.
here.
We do. Let's pause it there. Dang. Okay. All right. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's swinging a little bit, but it's not too
We
bad.
got it before it did that.
Okay. So that's 3.78 seconds for 10. Which means for 10, so that means our period is going to be, I just divide that by 10.378 seconds for one cycle. Okay.
So find the angular frequency. Go.
We're going to let them do that, right?
Yes.
Okay. All right, so.
Pause this until you got it.
Do it. Plug it in. Plug in those numbers, okay? And there is your equation, right? And we're using this one right there.
Yep.
Okay. All right, so what is the spring constant for the spring?
So once you got the angular frequency, how can we find, this is a different spring than those other ones that we've been playing with.
So once you've got the angular frequency right here, we want you to find this now. Right? And we know what the mass is, so make it happen.
So go ahead and do that.
Do it. Okay. All right, so let's go ahead and give you a definition that you've been waiting for since the beginning of this unit. Simple harmonic motion is a periodic motion where the restoring force is directly proportional to the object's displacement from and acts towards the object's equilibrium position.
That means the more you stretch the spring, the stronger the force is. That's proportional to the displacement. And the force is always in the opposite direction of the displacement, back towards equilibrium.
And, you know, everything that we've been doing so far is simple harmonic motion.
That's right.
Today we're going to talk about a simple pendulum, and it also shows simple harmonic motion. So, we're going to go ahead and show you two pendula.
It's a Latin word, sorry.
And tell me, what do you notice? So here they are in all of their glory.
Got a string.
Okay. So you got string. We got pendulum 1 and pendulum 2, and I'm gonna pull them back here. And let me go.
Write down your observations. What's the difference between the two?
So you might notice that this one is going faster and this one is going slower.
Yeah.
Yes.
Yep.
Okay. So my next question for you guys is, what determines the period of oscillation for a pendulum?
I think we can make a statement based on this simple observation.
Yeah, I mean, what's different between this pendulum and this pendulum? Well,
longer string, shorter string.
Longer string, shorter string. So essentially, what is the relationship between the length and the period? Well,
longer string, period is a time for one cycle.
So the longer the string, the longer the period.
Yep.
right? The more time it takes more seconds it takes for one cycle. And now they're starting to go in little circles here. So I'll bring this back up here. And I've got words to match with that.
By the way, before we go on here, I notice that they're at equilibrium now.
Mm-hmm.
And so the equilibrium point is kind of like in the middle, yeah?
I would say
And
so.
if you pull it in one direction, what's the direction of the force on it?
This way.
Okay,
Oh, no.
but what's
the direction of the force is down.
Well, but it can't go straight down because of the string.
Mm-hmm.
So when you let go of it, what direction does it go?
That way. That way.
So it's simple harmonic motion, and the force that's acting on it is towards equilibrium, because if you stop it on the other side, what's the direction of the force? Towards equilibrium. So simple harmonic
okay, yeah.
motion
I like
is
that.
produced by that restoring force as it goes back and forth.
Let's see. So the frequency of a pendulum depends on the length and the acceleration due to gravity. Woohoo!
That's right. It's not a spring. It's gravity that's exerting the force on the pendulum.
And that's what Mr. Boykin was talking about back there.
Yeah.
Right? Okay, so angular frequency. Oh my God. You know, we've been using this equation.
We could find the angular frequency of both of these.
We could. We totally could. Now, for small amplitudes, and I'll talk about what a small amplitude means in a moment, we have this equation as well. So if we wanted to figure out the length of the string, we have an equation for that. What is G here?
It's the acceleration due to gravity.
Acceleration due to gravity, okay? And when we say small amplitude, you know, a small amplitude would be something like, you know, like this.
Yep.
Okay, going back and forth. A not small amplitude would be something that when you let go from up here, right? Oh.
And you can see all kinds of strange things happen when that happens.
Yeah. So we don't want to do. That's how we talk about small amplitudes. Okay.
So solve this equation for t.
Solve. Ignoring this
Ignore
part.
that.
Yeah. Okay. So ignore this part over here. Solve it for t. Should we do this one with them?
You guys go ahead and Ms. Moore will show you what the answer is.
Yeah. Okay, so we got 2 pi over t equals the square root of gravity over the length. Okay, now we're solving it for t. Okay. The first thing I'm gonna do is.
I do the Boykin flip.
I was gonna say, should we? Oh no, right here.
Yeah, I just take the thing on the top and switch them like that.
2 pi do. Okay, of G over L equals T like that. Dang, that's easy.
It is.
And when we're solving, when we're plugging in G here,
Yep.
we can't have a negative under there. So our gravity is going to be positive 10 meters per second squared.
Yep.
Cool. Okay. All right. So for a pendulum of length 1 meter, find the angular frequency and find the t.
Okay, the L is 1 meter. Could we go back to those? Oh, we've got it right.
We've got it right here, right? So the first thing we're going to find is this one right here. And let's see, we've got the period, right?
Yep.
Okay. Oh, what?
No, we don't have the
don't
period.
Do we need to get the
We're
period?
just going to use the square root of G over
Oh,
L.
okay, yeah, we will. Okay, so I'm going to go ahead and say.
And that's here on Earth, where the acceleration due to gravity is 10 meters per second squared.
Okay. Do we have the length of the string there? Oh, 1 meter, right?
Yeah, it's 1 meter.
Okay, and so let's just go ahead and plug this into our handy-dandy calculator. So, but as you guys see,
It's going to be the square root of 10. It's going to be 3.
Why did I put 2 pi in? Oh, is it 3?
Well, I don't know. What's the square root of 9 is...
3.16. 3.16. Okay, so 3.16
radians per second.
Per second. Okay, so for a pendulum, that is our angular frequency. Now, let's go ahead and find t.
By the way, just for a moment, notice that this mass cancels this mass, and the unit is something over second squared. And you take the square root, and it's radians per second.
Okay.
Now
And
find the period. We know the angular frequency.
We
It's
know this.
3.16.
so now we're going to use this equation right here, right?
Yeah.
Omega equals 2 pi over t. We're going to flip these bad boys. T equals 2 pi over omega, and omega is 1/6 radians per second. Oh, I hate when I do that. Okay, so 2 pi divided by 3.16. Okay, and I get 1.99.
So in order to get,
Seconds for a
so
second.
if you've got a 1 meter, it's going to take just a sneeze under 2 seconds to swing back and forth.
This is the meter. Okay.
You know what? We can kind of test that.
Yeah? Is this a...
We'll see, we've got a meter stick on here,
Oh, yeah, okay.
and there's the top.
It's almost a meter, yeah?
Yeah, we just need to lower it down some. So you loosen this.
Uh-huh. Oh, I see. Tell me when.
A little more. A little more. A little more. But I'd take it all the way out to the end.
Right there?
A little more. There you go. Stop.
All right. Ta-da! Okay. Look at that.
All right, so there's a meter. And let go. And boom. 1, 2, 3, 4, 5. I'm bored. I'm stopping it. Okay, that's 10.08.
Ah.
For 5, half of that would be just about 2 seconds. Yeah.
So, oh, yeah, perfect. Nice.
Sweet.
Not perfect, but almost perfect. Okay, nearly perfect. Mr. Boykin is really perfect.
Yeah. I'm not going to go to 10. It was too long.
Okay, so that's cool. So what I notice is it doesn't depend on the mass there.
Nope.
Which is kind of cool. It doesn't matter like how far I pull it back.
Nope.
Right?
Well, within limits, there is. If you pull it way, way back, different things, because it starts to fall down and you don't get simple harmonic motion.
Yeah, and that's cool because, it has to do with gravity and all that stuff.
Acceleration due to gravity.
All right, so how long must a pendulum be to have a period of 1 second?
Go ahead.
Make it so.
You've already solved for the period, right?
Yeah, so...
So here we are on
period.
Earth.
Oh, wait.
Pause this and do it.
Wait, no, we want to solve for L though, don't we?
Yep, we want L.
Yeah. So we haven't solved for that yet. Shall we help them with that solving?
Well, you've got this equation right there. 2 pi over the period is equal to square root of g over L. Solve that for L. Pause it and make it so.
Solve that for L, and then
And
the
we'll
T
do
is,
it now.
This is 1.
Yeah.
Okay. And then wait, was there one more?
Yes.
Are we gonna do this with them, or do we want to go to
Well,
the
let's
next
do
one?
it with them.
Okay.
What the hell?
Okay. Okay, so let's get rid of all this stuff here. This one. Don't need that anymore. Okay. All right. So if I'm gonna solve this for L, I'm gonna rewrite it over here. 2 pi over t equals the square root of g times L.
First, you got to square everything.
Yeah, I'm gonna square it all to get rid of the that thing right there. So that's 4 pi squared over t squared. Now, do you like to leave it in the parentheses, or is
No,
how you
I
wanna
just
do
leave it just like that.
Okay. Equals g over L, and I'm gonna flip this.
I like that. I
Yeah,
would do
so-
exactly the same thing.
So t squared over 4 pi squared. That's a 4. Equals L over g, and then I'm just gonna put the g over here.
Yeah.
Okay, multiply by g on both sides. Get over there. Okay. So now that we've got that, let's go ahead and
So
plug
the
this
period
stuff
is
in.
1 second.
Yeah, this is gonna be 1. Okay, so this will be 10 meters per second squared times, and then that's gonna be 1 second, all over.
And when you square 1, you get 1, right?
Oh, I forgot it was squared. Sorry. Whoops! Don't be like this more. Don't forget to square it. Okay, but yeah, so we've got 10 divided by 4 pi squared.
You'll have to use parentheses on the
Yeah,
bottom.
4 pi squared, and I get 0.225. Okay.
So it's going to have to be 2.5 meters long.
Wait, what'd you say?
So the-
0.25, yeah. I thought you said something different. Okay. Okay, sweet. So
Yeah,
in order
0.25
for it to
meters,
have
yeah.
a period of 1 second, it has to be 0.25 meters long.
I wonder if we should.
Could we try and make this one up? So we could bring it up to here.
Yeah.
Okay. Where is this? Is this it right here?
Yep.
Okay. So right there is the length.
You want the center of the ball at
Right there.
0.25.
Okay, and then we'll get rid of this. I see how you draped it over there. Okay, so
Swing it.
here we go.
That's too
Ooh.
far. Just a little bit.
Oh, you see, oh, why is it so wobbly right now? You see that? Okay, you ready?
Yeah. On. Okay. And start that again. 1, 2, 3, go. 1, 2. Who's the physics teacher in the room here? Mark, get set, go. 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Okay.
I got a 10.11 seconds,
That's it.
which is within the.
If we divide by 10, we get 1 second at that length. Woohoo! That is cool.
Yep.
I'm excited. Okay. Make it so. You guys see that? Here it is. We made it so. Okay. How long is this string?
Well, first, not that one.
Yeah, not this one.
Just
I'm
let go of it.
Get a little set up here.
I gotta come around on this side. We mean this string up here.
How long is this string? Now I can't just measure it.
No, it goes up to the ceiling and drops down.
And we have a 1 kilogram mass that we're gonna hang on the end of this right here. Okay.
Yeah.
So what information do we need?
Well, we're here on Earth, so the acceleration due to gravity is 10 meters per second per second. And didn't we solve for L a minute ago?
Yeah, right here.
So what is it we need?
So if we solve for L,
We need
these
the
are things we
period.
need. All we need is the period. Okay. So get your calculators ready. And
Just pull it.
Right here?
That's enough right there.
right there. Okay, ready? Tell me
Just
when.
let go. Oh snap. Oh snap. And go. And stop. Oops, it didn't stop. Okay. Here, you do it.
Okay. just one thing.
Yeah.
Okay, hold on. And start. And stop. Okay, I got 3.33.
3.33 seconds. So your assignment is 3.33 seconds.
Find the length of the string. And then we actually have a little more homework for you. It's your lucky day. Okay, page 277, number 44 and 45. So do this and find the length of that string that we just did. Go get them, Tigers.